Section 32 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by James Curran. The Science, History of the Universe, Volume 1. Edited by Francis Rolt-Wheeler. Astronomy. Chapter 21, The Constellations, Part 2. Of the individual stars, though not the brightest, perhaps the most important to us is Polaris, the North Star, or Pole Star, which is in a straight line with the two stars marking the bottom of the Dipper, which are termed the pointers. It is 5 times as far away as the interval between the pointers and very nearly occupies that point of the heavens towards which the north pole of the Earth's axis is directed. To the observer on the Earth, it appears to mark the north. Its position, however, varies with its latitude. It has a certain circular motion due to the slow shifting of the direction of the Earth's axis, known as precession, so that in the course of some 12,000 years it will be displaced from its position as the pole star, and Vega, a pale blue star of the first magnitude in the constellation Lyra, will assume its place. With the conception of the cellular sphere held by the ancients, it was not difficult to assume that the stars were studded about the sky at a considerable distance, yet nothing beyond noting their apparent distances from one another as expressed in angular measure. But little attention was paid by the early astronomers to their remoteness from the Earth. Indeed, they assumed them to be very remote, and Aristotle remarks, quoting the opinion of the mathematicians, that the stars must be at least 9 times as far off as the Sun. Timocharis and Aristillus, both of whom flourished in the early part of the 3rd century BC, were the first to ascertain and to record the positions of the chief stars by means of numerical measures of their distances from fixed positions on the sky, or in other words, to supply data for the first real star catalogue. But this did not afford any adequate idea of the absolute or relative distance. After the death of Hipparchus, it was recorded in an early textbook of astronomy that the stars need not necessarily be on the surface of the sphere, but may be at different distances from the Earth, which, however, could not be determined with the means at hand. In the works of this period, the conjecture is also hazarded that the Sun and the stars are so far off that the Earth would be a mere point when seen from the Sun, and quite invisible from the stars. In the Almagest Talmudi, in a series of postulates, Book 1, Chapter 2, state that the Earth is merely a point in comparison with the distance of the fixed stars, and he believes it is most rational to assume that the bodies like the stars, which seem to be of the nature of fire, are more likely to move than the solid Earth. Copernicus believed that the stars must be at a very large distance as compared with the size of the Earth, because the horizon apparently divides the celestial sphere into 2 equal parts, and the observer appears to be at the center of the sphere, no matter how much he moves on the Earth, so that the distance moved is imperceptible as compared to the distances of the stars. He maintained that the stars were all at the same distance from the Earth, and according to his theory, some annual motion of the fixed stars should be observed due to the alteration of the Earth's position in its orbit. As this was not noticed, Copernicus assumed that the distance of the stars was too great to cause any appreciable motion. The instruments of those days were quite incapable of detecting such a small amount of motion, requiring, as it did, greater refinements of observation. The positions of the stars were carefully noted by Tycho Brahe in the great celestial globe 5 feet in diameter, which, in those days, served as a star chart, with a quadrant or quarter circle having the radius of about 19 feet by which the angles could be read to single minutes. He made a number of observations of the chief star in Cassiopeia, as interest in the constellation was aroused by the appearance in it of a bright new star in November 1572. As he was unable to determine any perceivable parallax, he assumed that the star must certainly be further off than the Moon. This discovery was important as indicating that the changes could occur in that far distant realm of the fixed stars, which hitherto was believed to be constant in both the appearance and constitution. This was corroborated in 1604 by Galileo in the case of a new star in Serpentarius, which he demonstrated was at least more distant than the planets. Galileo, in his Dialogue on the Two Chief Systems of the World, brings out the fact that the angular magnitudes of the fixed stars, which were most difficult to determine, are in reality almost entirely illusionary, and indicates a method known as the double star or differential method of parallax, by which the motion and the distances of two stars at different distances from the Earth can be measured. At the beginning of the 18th century, though 2,000 of the fixed stars had been observed and their positions noted, nothing was known of their distance beyond the fact that it was so very great that they exerted no sensible influence. It was not until the time of Sir William Herschel that a successful attempt was made to determine the parallax of a star and to ascertain the distribution of stars in the heavens. Herschel assumed that the distances of the stars depended upon their brightness. In the case of a star barely visible with an 8-inch mirror and one just visible with a 4-foot reflector, he assumed that the second was 6 times as far off. By making a series of measurements, he estimated, for example, that the faintest stars visible to the naked eye were about 12 times as remote as such a bright star as Arcturus. If Arcturus was removed to 900 times its present distance, it would just be visible in Herschel's 20-foot telescope, while more clearly seen in his 40-foot instrument, which he assumed would penetrate about twice as far into space. These observations of Herschel were far more productive of results in other fields than the determination of stellar distances. It was by Bessel's memorable observations that the angular motion of the star 61 Cygni was determined in 1838. His calculations showed that the distance of this star was about 400,000 times the distance of the Sun, or 400,000 times 93 million equals 37,200,000,000,000 miles. This was the first direct solution of a problem which long before the day of Aristotle had puzzled astronomers. If it is difficult to realize the distances of the planets from Earth and the Sun in the solar system and the extent of their orbits, what must be said as to the distance of Earth or the Sun from the stars? For this, all previous scales of measurement were deficient, and a new unit of measure, itself of bewildering magnitude, had to be devised in order to realize distinctly the immense intervals of space separating the stars from the Earth. Miles or kilometers were naturally inadequate for such a task. The luminous body emits waves which are propagated through the ether at a rate of 186,300 miles per second, or, in round numbers, 6 billion miles a year. Accordingly, the light year was taken as our unit in discussing the distances of the stars. Thus the light from Bessel's star 61 Cygni would take more than 6 years to reach the Earth. But 61 Cygni is not our nearest star. Subsequent investigation show that this place belonged to Alpha Centauri, which is 4 1/3 light years from Earth, and probably 10 billions of miles nearer to us than any other member of the sidereal system. Sirius is twice this distance, or 8.5 light years. Vega is about 30 years, Capella about 32, and Arcturus about 100. But not for every star are these distances known. They are determined by measuring the parallax whenever possible. To quote Dr. Otto Klotz, parallax is the apparent displacement a body suffers by change of place in the observer. With the highly refined instruments and methods, notably the heliometric and spectrographic, definite results are being attained for the comparatively few stars of the myriads that strew the sky and mark a milestone in achievement of practical astronomy. Bold indeed was the undertaking when man first attempted to measure the dimensions of the earth, but bolder was it when he projected his measuring rod to the sun. What shall we say when we find him rushing off, measuring rod in hand, at the rate of 186,000 miles per second, and, after 4 1/3 years, reaching the nearest star, Alpha Centauri, a bright star of the southern hemisphere? This tremendous distance, quite beyond our grasp when stated in miles, is expressed by saying that its parallax is 0.76 degrees. Many of the brightest stars are found to have no sensible parallax, while the majority of those ascertained to be nearest the Earth are of the 5th, 6th, or even 9th magnitudes. If the parallax and the distance of the stars are determined, it is possible to make some approximation of its mass in the case of binary stars revolving in known orbits. In other words, if we can determine the number of seconds of arc which separate the two members of a binary system, and translate this distance into millions of miles, and then measure the period of rotation, we can find their combined mass in terms of that sun. For example, the components of the double star Alpha Centauri, to which we have referred, revolve around their common center of gravity at a mean distance of nearly 25 times the radius of Earth's orbit. As they require 8 years for a period of revolution, the attractive force of the two together must be twice that of the sun. With single stars, such a computation cannot be made. Knowing their parallax, however, it is possible to estimate from their size and brilliance some of these splendid stars in the heavens, such as Canopy, Betelgeuse, and Rigel, and to realize that they are thousands of times greater than the sun, and suffer in comparison by their infinite distances. For it must always be remembered that the brilliance of a star depends not only upon its intrinsic brightness, but also upon its distance from the Earth. For 5 other of the visual binary stars, data are available for computing their masses. The Sirius, which radiates 32 times as much light as the sun, is supposed to have a combined mass of its two constituent stars of 3.7 that of the sun. Procyon, 0.6 that of the sun. Cassiopeia, 1.8. 70 Ophiuchi, 1.8. And 85 Pegasi, 11.3. The average distance of the stars of a pair of these in the above list from each other is 23 times the distance of the Earth from the Sun, or a little greater than the mean distance of Uranus from the Sun. It is probable, however, that most double stars are further apart than this, but it is evident from the stars considered that the average mass of a pair is 3.5 times that of the Sun, while the average radiating power is nearly 6 times as much. End of section 32.